Hi there everyone. In this video we are going to be looking at exponential functions and some applications of exponential functions. In particular, this situation here where we're in a situation where the rate of change or the rate of growth of a population, or going up or down, is proportional to the amount in the population itself. So that's this differential equation right here. It says the rate of change dp dt. A lot of the time when we say rate, we're talking about with respect to time. So the rate of change of the population is proportional to or equal to some constant times the number in the population. So the rate of change of the population of China, where there's 1 billion people, the rate of change is big. The rate of change where you've only got 5 people in a little colony, the rate of change is very small. So this differential equation is really helpful to describe those kinds of things, and it crops up all the time. So what we need to know is that when we have that situation, the solution of that differential equation looks like this, okay, and we get the exponential function. So just let me kind of take you through a little bit of a justification of that. So if we start with our formula, I'll use AE to the kt. So A is a constant, K is a constant, T is time, we know what E is, and P is the population. So if we do the derivative here with respect to T, dp dt, we'll just leave the A there. We know the derivative of e to the power of anything is just e to the power of anything, times by the derivative of k times t. Now we're doing the derivative with respect to t, so the derivative of that thing there would be k. Alright, now a bit of rearranging there. I'm going to make that k out the front and ae to the kt. Alright, so you will recognise that ae to the kt is just p. So I could write this as k times p. So there we go, there's a little justification that shows you that when we have ae to the kt, that when we do the derivative we just get k times the original value. So kind of going backwards there, but so if we start with a situation where this is the case, the derivative is k times p, then we know that this is the solution for that differential equation. So a couple of examples quickly. So we've got a factory producing 10,000 units per year embarked on a productivity campaign by identifying problems in production. As a result, the production per year increased according to that equation. So you're looking out for something where you've got the derivative is k times p in this case. So we know straight away our answer for A. Find an equation for the rate of production. I know it's going to be P equals A e to the 0.02 t in this case. And that 0.02 is coming from that there. That's our value of K in this case. Now we don't have the value for A there. So we know that when we started it was producing 10,000 units per year. So when t is equal to 0, P, the production was 10,000, right? So if we put that into this thing here, we get 10,000 for P equals AE to the 0.02 times 0. So this is 0. E to the power of 0, of course, is 1. So all of this stuff here is 1, and we just get that A is 10,000. Okay? So 10,000 e to the 0.02 t. This represents, if we were talking about money, this is continuous compounding interest 2% per year. So this fits that model as well, whereas the rate that your money is growing is always proportional to how much money you've got there. So if I've got $2 in the bank, my money is growing at a small rate. If I've got $2 billion in the bank, my money is growing much faster. So hence this model also fits this one here. Okay, find the number of units produced in the 7th year. So now we can just get our calculator out and say, okay, the number of units is 10,000 e to the 0.02 times 7. The number of units produced in the 7th year. And that works out to be 11,502.737, which we would never write as an answer because it's asking for number of units here, not like area or surface area or height or weight or something like that, which is continuous. This is an exact number. So we'd say 11,503 units for our answer. And C, find the rate of increase after 7 years. The rate of increase. Okay. So the rate we know is dp dt. Okay, that's the rate of increase. Now we've got our formula. It is right here. So I've just got to differentiate that with respect to t. So that's 10,000 e to the 0.02 t times 0.02. Okay, the derivative of 0.02 t with respect to t is 0.02. So now I need to get my trusty calculator and do 10,000 times 0.02, which I probably could have done in my head, which is 200. So 200 e to the 0.02 t. That's the rate of change of p in this case, the number of units. So the rate of increase after 7 years, we just substitute t is equal to 7 in there and get our calculator out. That gives us 230.054. So I'd say around about 230 units per year are the units there, because we're talking about a rate of change. So at that exact time, and this is changing all the time, the rate of increase is 230 units per year going up. Radioactivity is another great model for this kind of relationship, this exponential decay. The more you've got, the faster it's decaying. So if you've got this big molecule, millions of molecules, the rate of decay of these molecules is great. When you've only got a few, the rate of decay is small. So in this case, we're talking about decreasing at 9% per year. So let's come up with the mass, the equation parts of all this. Okay, so let's say we could just choose any letter here. Let's call it M for the amount of isotope. Okay, it's going to be A, E to the K, T. We know that because we know that it's decaying continuously and it's 9% per year. So I know that the K is going to be 0.09. So let's write that down. So M is negative 0.09 T. Or you could say it like this: dm dt, the rate of change of m, is equal to negative 0.09 T. Okay, you should be familiar with being able to go through that one on the right and that one there on the left. That's a solution to that one there. Okay. 1 kilogram of this isotope is produced in a particular industrial process. That means we start with 1 kilogram. So without going through all the process, I could just say in here, this is 1 when t is equal to 0, so that gives me that A is equal to 1. Okay, so I'll just go and rub this out because I know that A is equal to 1. So now I've got my formula. Now I can start answering the question: how much remains undecayed after 20 years? So the mass is going to be E to the negative 0.09 times 20. Okay, and we started with 1 kilo. So if we do that, we get 0.165 kilograms. Okay, so we started off with 1 kilo. After 20 years, we've got 0.165 a kilo, or about 165 grams. Last one here, savings account 1. Here we've got 8% per interest compounded continuously. So the rate that your money is growing, let's call the amount of money you have A. So this is the rate your money is growing at, is equal to 0.08 times A. Only in this situation where it's compounded continuously. Okay, so that means that the amount of money is, I'll use like this, A naught, the initial amount, E to the 0.08 T. And here the initial amount is $400. Okay, so when T is equal to 0, A is equal to 400. So we could just put that in there like that. So then we come up with an equation. Brilliant. If the interest rate is maintained for 5 years, what will be the balance of the account at the end of this time? So A is easy. We're just going to substitute in e to the 0.08 times 5. And that gives us $596.73. If you said $597, that would be fine as well. And part B, how many years, correct one decimal place, will it take for the balance in the account to treble the initial deposit? So, treble our initial $400 deposit means we're going to have $1,200. So we've got that. So we're solving, we just solved this on our calculator really, guys. If you wanted to, you could do that. We don't know how to use logarithms yet, so we're going to get our solve key out, and that works out to be T is 13.7 years.